Anyway, so the slides will be posted. I'm debating posting the video. I'm honestly going to leave it up to you guys because it's not fair to you that you're here and you're participating and everyone else gets to take advantage of your participation. So I'm going to leave it up to you guys at the end whether you're okay with me posting the video to Canvas. I personally, if this was me and I was in your situation, I'd say fuck no, they should be here. But for everyone who's here and has to leave early, just put the message in the chat and I will, I'll send it to you for sure. But in terms of the people who are just decided to stay out till 3 last night and are super hungover right now and can't force themselves to get up, like for like no reason, I'm not like 100% okay with giving this recording to them just because they didn't want to wake up. You know what I mean? Unless it's okay with you guys. So that's my long answer to that. Yes, I'll absolutely send the list to the video. Send the video to people who are here. That's why I wrote your names down, and that's why I want to make sure everyone puts their name in the chat. All right, so moving on to lesson 3, unless there's any other questions. All right, so sweet. All right, so lesson 3 talks about 3D forces and unit vectors, which is kind of a big one, and the part where it starts to get a little bit more complex in terms of like the actual calculations you're responsible for doing. So there's that. The first thing to probably talk about is what a unit vector is, because I think that concept is still a little abstract for people. So a unit vector, like, is defined as a vector with a magnitude of 1 unit in the direction of a force, right? So that's a really fancy way of saying that it's a way of just describing a force's direction, right? So it doesn't take any change in the magnitude once you apply the magnitude to that vector. So it kind of acts as like, so you know how when you have a picture of a beam and there's a force pointing like 80 newtons up and then you have that slope triangle or whatever? So that will be very difficult to change into a vector in 3D. So not less so in 2D, but in 3D, it'll be hard to make it into a vector without doing it with the unit vector, because it just becomes so much more complicated in terms of the components. So the idea is if you just use a vector to describe the direction and then find the magnitude of that direction, you can normalize the vector that you just found to 1, so that when you apply the magnitude, it doesn't change the magnitude given in the problem at all. Does that make sense? Going into the like steps involved, you're gonna generally be given some information about the magnitude, usually like what the actual magnitude is, and some kind of information on the direction, whether it's like from point A to this component or like a slope triangle or an angle itself. You'll be given some information about the direction. So the nature of a vector is that it already has a magnitude and a direction inherently built into it. So like if you write something in vector form, it's the magnitude in each direction, which means that it takes both of those components required for a vector quantity and satisfies it. So the first thing I would do is find a vector that describes the direction that the force is going using trig. So that would be considering the slope triangle or considering the angle you're given, something like that, right? We'll do something about, like, we'll do a practice problem with this later, because this is something that goes into your table for 3D forces, right? Or 3D equilibrium, I'm sorry. So the second step, once you find a vector describing the direction, right? By nature, if you're using a 3, 4, 5 triangle, right? It says it goes 3 in the x direction and 4 in the y direction, and say 0 in the z direction. That has an inherent magnitude to it. So you're using the simplest way to get the vector for the direction, but that vector that you got has an inherent magnitude. So if you multiply the magnitude of the force straight into that position vector you just got, it's going to scale the magnitude of the force itself, which changes the amount that that force is acting on the body, right? So because of that, you have to normalize the position vector, which is done by finding the magnitude of the position vectors, which is the square root of x squared plus y squared plus z squared, right? You've been doing that all semester now. So that's how you find that. And then you find the unit vector by dividing the vector that you found for the direction by its own magnitude, because anything divided by itself is 1, right? So that's how you would get the magnitude of the unit vector to equal 1. You just pick a vector, divide it by its own magnitude. And then lastly, you're going to multiply that unit vector by the force it's given, because if you multiply the magnitude of the force by something with the magnitude of 1, you're not changing the magnitude of that force. So after hearing all that, I know it's either 100% clear for you, or I just made it a lot muddier by going into the conceptual side of why it's necessary. So if anyone has any questions, now is the time. Because I promise you, you're not the only one with your question. Also, I don't think I've told you guys this yet, but in terms of, for the people who didn't hear it, I'm going to try to get extra credit for you guys for coming here today. So I'm taking a tally of how many questions people are asking related to concepts, and I'm using that as an argument, hey, look at how involved they were, blah, blah, blah. They deserve extra credit. Because of the 77 kids in this class, there's only 25 of you here. So that's kind of impressive to me that you guys showed up. So yes, see, facts. Okay. So if no one has questions on this, I'm going to move forward. Okay. Looks like I'm moving forward. Sounds good. Okay. So lesson 4 talks about 2D moments. This is the first time a moment is introduced in the lesson sections. And I don't know if you guys remember what a moment is, but it's essentially a quantity describing how a force makes a body want to rotate, right? So if you put your pen on the table in front of you, right? Take one finger, right, and push along either the, push right along the cap of the pen, right? It makes it pivot, because even though you're applying a force directly at that point straight forward, it causes it to rotate unless there's another force counteracting it, right? So that's the idea of a moment. It's quantifying how much pushing on the pen cap makes that want to rotate. So think of a door, right? This was an example I used in Liao's class, but for everyone in O'Neill's class, you haven't heard this yet, I don't think. So if I'm going to open a door, right, it's connected at a hinge, which means essentially there's a moment about that hinge because that's where it's rotating from, right? If I walk up to the door and push at the hinge, it's not going to open because that point is fixed in terms of how it can rotate, right? But if I push halfway through the door, I can open it, but it's obviously not as easy. And then if I push at the handle, it's super easy because I have a lot of leverage, right? Which is why the door handles are all the way opposite the hinge, because that's the most effective way of using it. So that concept of how far I am from the hinge is what we call the perpendicular distance between where you're applying the force and where the moment is generated, right? So if I'm opening the door with a handle, the perpendicular distance is the distance between the handle and the hinge, and the force is how hard or soft I'm opening the door, right? So the idea with two-dimensional forces, I know O'Neill loves vectors, but in reality, on an exam, he's not going to say use vectors to find this 2D problem, whatever, right? You are literally given a question and how you solve it's up to you. My advice is that unless you really only know how to use vectors, don't use vectors with two-dimensional moments, because it's going to make it so much more complicated. Because some of your values will be in scalar form from the forces, and some of them will be in vector form if you do the moments with vectors. So the equation for the scalar moment, or the moment that I would recommend you do here, is the perpendicular distance times the magnitude of the force. So all that means is that instead of breaking it up into a vector, blah, 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 doing the cross product, whatever, you can literally just say, okay, I know the handle is 3 feet from the hinge and I'm pushing it 5 pounds. There's that. My moment is 15 foot-pounds. So there's that. The advice that I have for you is that most of these forces, because it's the exam and they want to make sure that you know how to do things well, are going to be at an angle. Again, the first step for every problem that I would recommend is to break up the components, or break up the force into its components, because I promise you I promise you that it'll make it so much easier to find the perpendicular distance, because that's the distance that's going to be labeled on the diagram you're given. So for the questions in the chat, one says, would we be given a force in the XY direction but only need the component X, or something like that? I'm not 100% positive that I get that question, but you're going to be given, you might need something in terms of, like, you might be given a diagonal force, but the X component goes through the point you're taking the moment at, right? So in that case, you're only going to need the perpendicular, or the vertical component, because the perpendicular distance of something whose line of action goes through the point you're taking the moment at is 0, right? So that's equivalent to me pushing diagonally on the door, but only some of it goes through the hinge, right? So there's that. Does that clear that up? Okay, cool. The second question is, do moments only occur on non-concurrent forces? Yes. So essentially, if you're pushing on a point, if I have 6 forces all acting on one point, there's no perpendicular distance. So a moment will only occur where there are non-concurrent forces, which is why in an equilibrium problem, if you have 3 unknowns at one point, you should take the moment there, because none of those forces will be causing a moment at that point. So none of those forces have to be considered, which means you can find other unknowns later on. That will be in an example later on. PJ's question, are we going over a moment problem later? Yes, we are. Well, maybe not a moment problem specifically from lesson 4, but there's going to be a problem that has moments incorporated into it. And then last question that I have so far, so moment is a dot product and not a cross product. So in 2D, it's just simple multiplication. In 3D, it's a cross product. And if anyone still has not put that program into their calculator, do not leave this meeting before you put it in your calculator. But yeah, no, so it's a dot product. It's not a dot product ever. So dot product is not at all related to vectors. I mean, moments, I'm sorry. Let's see. Yes, so putting the function into your calculator, it is on the Canvas page in the administrative section of the modules. And then, let's see. So when it comes to doing 2D and 3D moments, for 2D, stick to theta. Yeah, exactly. So for 2-dimensional moments, you want to stick to like the perpendicular distance times the force, and then for the vector 3D, stick to the position vector cross the force vector, which we'll go over in just a second, because that kind of gets confusing too. Any more questions on 2D moments? If you have questions on moments in general, I would wait until I go over 3D moments, and then if I don't say something that covers it there, then ask the question. Sounds good? Sounds good. Okay, so 3D moments, very similar, still describe how a body wants to rotate after a force is applied at a certain point. So that's exactly the same. Calculating the moments, again, you're going to do this for the rest of the class, so get used to it. For 3D, you do need to use vectors. So it's going to be the moment is equal to the position vector that you generate cross, I know that's an X, but it's supposed to be a cross F, right? So R is going to describe the position from the point that you're taking the moment at to any line of action on the force. We're going to see that later on, and I'll discuss it again later on. But again, when you're filling out the table for 3D equilibrium, the first column is, here, I'll just scroll forward. Okay, so this table right here, right? Actually, probably better here. It's the list of the forces. This R right here is what goes into the cross product. This R describes the distance between, or the direction from the point you're taking the moment at to the force itself. So in the case of this problem, right, you ultimately take the moment at A, so the position vector R is going to describe how far this force is from A, and then how far this force is from A, right? That being said, this vector F still has an inherent, like, you have to describe some kind of direction, right? So this whole F section right here describes the stuff in lesson 3, right? So this is a matter of doing lesson 3 in this table. So you find a vector describing how the force behaves. So this one is going, we'll go with this one. This one's going straight down in the Z direction, right? So it's going to be 0, 0, 150, right? And then technically what you're supposed to do is find the magnitude of that vector, which is in this case 150, and then you divide, sorry, my mouse keeps quitting. You divide the vector you find by the vector you're given, or the magnitude of that vector, and then you find the unit vector. So in this case, since there's only one term, it'll work out to the same thing at the end here. But anytime there's more than one term in that vector that you find for the force itself, not for this one. Anytime there's only one vector or one force in the direction that your force is going in. So if there's two zero components, I'm sorry, I'm tripping over my words. If there's 2 0 components within that vector, the magnitude is just going to be the third component, the third non-zero component. Your unit vector is going to be 0, 0, 1 in this case, and then once you multiply the magnitude that you're given back into that, it'll just be the original force you found here. So in this case, it would be 0, 0, 150, or negative 150, I'm sorry. So the unit vector would be 0, 0, negative 1. And then once I multiply 150 back into that, it's 0, 0, negative 150. So going back here, does that kind of make sense? So essentially in this problem, you're going to have 2 different position vectors. This one is going to describe how far from A the force is, or how far from whatever point you're taking the moment about the force is. And then the position vector generated within this calculation describes how, or in what direction the force is going. Does that make sense? Questions at all?
So the F would be 0, 0, negative 150 in the case you were going over before?
Yeah.
All right.
That one was easy to calculate because it was, what the heck? I'm having technological difficulties. So yes, so this one is 0, 0, negative 150 only because it's going straight down, right? But if you look at this case, they'll be going at an angle, right? So in that sense, it'll have components in each direction. This one will still be going straight down, so that one's still going to be 0, 0, negative 80. But these two, since they're at an angle, will have other components. And that's why you need to find the magnitude, because in this case, it won't be the same as the vector you come up with.
Okay.
Any other questions? None whatsoever. Okay, that's not what we're on. Okay. It is. All right, so the next topic that was brought up is couples, right? So the idea behind a couple is that if you have 2 forces acting in parallel and opposite, or acting with the same magnitude in parallel but opposite directions, you're going to generate some kind of twisting form. So again, put your pen on your table, right, on your desk or wherever you're at. Push up on the pen side, or on the cap side, push up on the bottom of the pen, and the pen's going to pivot right about the middle of it, right? Every time you have forces going equal magnitude, opposite direction, you're going to have that same kind of rotation or spin or whatever. So because spin is generated, it's a moment, right? Which means you can use the moment equations we just talked about. So this lesson was the combined 2D and 3D, But again, if you're going to use, if it's a two-dimensional couple, use the perpendicular times the magnitude. If it's 3D, then use the cross product. Because it's, for the same reasons, it's much easier. In this case, though, so these formulas kind of mean something a little bit different in the event that it's a couple. Because like I said, if you push like that, the spin point, or like the part that the moment is going about, is right in the middle of the pen, right? So it's not about a different point, it's right in the middle of the pen itself. So it's between the two forces. For that reason, your D perpendicular is going to be the distance between the two forces. So when I opened the door, the force was at the handle and the moment was about the hinge, right? So that's why I had to go from the hinge to the door. Here, the moment is about the middle of, in between the forces itself, so you have to find the distance between the two forces. The magnitude of F is still the magnitude of the force, but so if it's two forces that are 200 newtons, you multiply the magnitude of F is 200 newtons, not the combined force. It's just the force of one of the couple components. And then lastly, for the moment in 3D, it's the same kind of concept. R is now a position vector describing the distance between the two vectors itself. But the magnitude is still the same. Does that make sense? Preguntas, anyone? For the 2D case, we should get the components of the force to know what the distance will be. Yes. So again, like I said, all the way back here, if you break up the components, you're not going to be given the perpendicular distance between the forces. You'll be given the vertical distance and the horizontal distance, depending on which one you need, but you're not going to be given the actual perpendicular distance. So like Michael said in his question, you're going to want to break up the couple itself, each individual force, into its components, because by nature, the components themselves will become couples. So if I have something pointing top left and something pointed bottom right, as long as they're the same force, like same magnitude, they'll still be a couple, because the amount of each force pointing to the top and to the bottom will ultimately be the one that becomes a couple, because they're equal magnitude still and opposite direction still. Does that help, Michael? Silence is a yes. So which F do you cross with R in 3D couple? Does it matter? So it shouldn't matter. Actually, what I can do is I can pull up. It depends on which direction you use for your R is going to depend on the F that you use. So let me pull up a worksheet that I found. I think I have to stop sharing my screen for a second so I can now share my desktop, but hold on one second. There was a problem that really kind of confused me because I kept getting it wrong, which pissed me off quite a lot. But let me pull it up real quick. Ultimately, what's going to happen is if you use the direction from one force to another, it'll depend on, or it'll affect which force you use. Okay, it's this problem. You use for your magnitude, because it'll be the same like value of your answer, but it's going to be a matter of a different, it'll be like negative for each value. So let me come here. So this problem, right? Let's see. Zoom in. Okay, so here it's Q and S are equal magnitude, check. Opposite direction, check. Parallel, check. Right? So if you look at what O'Neill wrote here, it kind of tells you what the deal is in terms of which force to use when. So let's see. So for this one, it went from B to H, right? So if you're going from the line of action of Q to the line of action of S, you multiply it by the magnitude of S. But if you're going from the line of action of Q, or of S to the line of action of Q, you use the magnitude of Q. Does that make sense? So whatever the head of your direction vector is, it's the that's the direction you're going to use for, that's the magnitude you're going to use. Does that make sense to everyone else? That was probably an important thing I should have brought up in the first time. But yeah, so essentially your position vector will be pointing at the magnitude you use. All right, so when you break up the couples into their components, do you still use the original perpendicular of the forces, or should you use different distance for the components? Okay, so the idea behind breaking up the forces in a couple into their components is essentially just to simplify the problem. So if you're gonna look at a different problem, is this the one that's like the little bendy thing? Where's the bendy? Okay, yeah. So here, let me pull up the original so it doesn't have as much right. So this problem was one that was super tricky because everything was at funky angles, right? The big hint in this problem is that the only distance that's really labeled in this couple right here is the x distance, or the perpendicular distance for the y components. So if I broke this force up into its vertical component and its horizontal component, the horizontal components are pointing at each other, which means they have a perpendicular distance of 0 because there's no distance between them itself. So that's how you know you broke up the force right, because if the dimension isn't labeled, you don't need it. Here, if you have the vertical component here and the vertical component here, the distance is the perpendicular distance between the two, which is the 3 feet. So I think, Audis, what your question was asking is, once you break it up, you use this distance, but that's only because you won't ever be given the distance this way. Or maybe I'm misinterpreting the question. But I guess it depends on what sort of, yeah. So really, the thing that you guys should start like looking for in the practice problems is how you're using the information given, because I promise if you blank on the exam, you sit down, you stare at the problem like, what is this even asking me? If you look at the question, you should have some kind of guidance on at least where to start, because you'll only have, or you'll have the information that you should use the information that you have first, if that makes sense. All right, so it's up to you guys. That went much faster than I thought it was going to go. Do you want to take a quick 5-10 minute break now, or do you want to just jump right in? Sean was, oh, okay, hold on. We're 50-50. Someone break the tie. Okay, so why don't we take a 5-minute break instead of a 10-minute break? 0 minutes. Simply 5. I don't know how to make a poll. I don't really know how to do that. And it'll probably take me 5 minutes to figure out how to make a poll. So in that 5 minutes, let's just everyone grab a snack, everyone go pee, whatever, and then boom, we'll be back. But I'm starting in exactly 5 minutes, so rush. Okay, bye-bye. Starting equilibrium. Boom. Things don't move. That's the entire nature of the entire first and second exam, is that things are not moving. So the overall force on the body itself will be 0. So essentially, if we're going back to the door example, the person pushing the door open and the person pushing the door closed, assuming that they're at the same exact point, door won't move, right? Because the forces perfectly balance themselves out. So that's the idea behind equilibrium conceptually. Talking about the steps for equilibrium, right? You're going to generally be given some kind of body, and that body will have a bunch of forces, dimensions, whatever. First step that I haven't put here is draw a free body diagram. I think for the first exam, they might put like pictures of the free body diagram that they want you to use next to it, like next to the picture given in the problem. But for the second exam, they won't do that. So you have to literally draw a free body diagram every single time. I don't know why, but they haven't stressed this a lot in this like semester, but it is for a grade. So the free body diagram is a component of the grade for the problem. So there's that. So do not start math until you've drawn a free body diagram. So the first step after that is to figure out from that free diagram what forces you have and what forces you don't. On the free body diagram itself, I recommend breaking the forces into their components, switching from the given picture to the free body diagram. So when I draw a free body diagram, I only have vertical and horizontal components of a force, right? So there's that. So from there, you'll be able to very clearly see what components of your force are unknown, or if you have too many unknowns, whatever. So the number of unknowns should be less than or equal to the number of equations you have. And in 2D equilibrium, you only have 3 equations. You have the sum of the forces in the x, you have the sum of the forces in the y, and then you have any kind of rotation in technically the z, but any kind of moment. So once you find your unknowns, you figure out if it's like what equations you have to use, right? So you can either sum the forces in the x and y direction, or what I didn't put here is you can take the moment at about a point. So I don't know if you guys remember, maybe it's the case in this problem. No, I picked that problem for a different reason. But I don't know if you guys remember this, but there was a problem that had like the ax and ay unknown, and then there was a by unknown later on at a roller, right? So you have 3 unknowns, so that works, you can solve it. But the problem is you can't just use sum of the forces because you have 2 forces in the y direction and only 1 equation to describe that. So essentially it'd be saying, an example that someone used in Liao's class actually that worked really well was, it'd be like saying x plus y equals 0, solve for x and y. Like there's infinite numbers of solutions to that. But yes, so the idea behind using the moment is to clear out one of the unknowns. So in that problem, you could take it at either point, but I usually take it at the point that has the most unknowns, because that clears the most unknowns out of your equation. So if you took the moment at A, the only unknown left would be the vertical reaction at the roller, right? And we'll do a problem, I think. Nope, these are both. Okay. Well, at the end, I can come up with a different problem if you want to do that. But the only other advice I have in terms of 2D equilibrium is to know reaction forces, right? Because if you don't know the reaction forces, you're not going to know what forces you need to solve for. So there's that. Any questions in terms of how to actually solve it or what it conceptually means? We're going to jump into an example problem, but while I get my stuff set up for that, if you have questions, now is the time. No questions. So everyone's going to get every single one of these problems perfectly right. Cool, that's what I like to hear. All right, so I might agree with you there in terms of there's no way that all of you are going to get everything right. How the hell do I get out of here? Okay, there we go. All right, so bear with me because this is the first time that I've ever written inside of a PowerPoint while I've been doing that, or while I've been live or talking or whatever. So this is the first problem we're doing. I chose this problem because I don't know if you guys remember it, but there's something like unique about this member right here. So BC is a two-force member, and I'll explain why that's important in a second, right? So the nice thing about this problem is that looking at it, it's complicated, but if you break it up into two separate bodies instead of just the whole cable, you can solve it much easier. So here you have point B, right? And later on you have point C. And there is some cable between them, right? My first advice, label every single force, right? So here you have the 15, and it's the sine and cosine of 15. Anyone real quick, and you have to unmute your mic because I can't pull up the chat while I'm writing, but if I'm going to find the x component of FAB, so the force from A to B, right? What would I use, sine or cosine?
Cosine.
Cosine.
Very nice. Anyone care to explain how they got that?
Because the 15 degrees is adjacent to the, I guess the line of action, you'd call that?
Yes, exactly. So remember how I said there's that little arc thing that labels tangent? That's this thing right here, right? So that the one that it's touching, which is in this case this component, is going to be the one that's cosine, right? So there's cosine. The one that's opposite that, which is the one that's over here, in this problem it's the vertical component, that's sine. Anyone have any questions on that? Speak now or forever hold your peace. Okay, so FABX, and that is, we said FAB cosine 15, right? And then what about FAB, or FABY, I'm sorry. Anyone? Sine or cosine?
Sine.
Yeah, so anytime you find the first one, the other one's just going to be the opposite. So in this case, it's FAB sine 15. Sweet. Anything else I need to add here? So that just took care of this force in the string right here. What else do I need to add?
The force pulling for the stoplight. I forget which one. I think it says 10 kilograms. We have to multiply that by 9.81 in order to change it into units of force.
Exactly. So the weight of that stop sign or stoplight is pulling the string down, right? Or the cable down. And Odyssey is exactly right in that in the problem, it gives us mass, right? So anytime we're drawing something on a free body diagram, we have to make sure we're putting forces on it, right? Not masses on it. So for that reason, exactly like he said, the weight of the stoplight A, or I guess that'd be smarter to call that stoplight B, and then the other one stoplight C. But the other, like the weight for stoplight B is going to be equal to its mass times its gravity, right? And I don't, what the hell, where did it go? I don't think that they're going to test you on this, but you have to be careful which unit system you're in. So 9.81 is only valid if it's in kilograms and newtons, right? So it's 10 times 9.81 is 98.1 newtons.
It's like 22.95 pounds, right? For like the American units.
I thought it was 32.2, but I
Oh, yeah, you're probably right. I just don't remember.
yeah, but I mean, they'll give it to you, I'm sure. Either that or it's probably somewhere in your reference if you need it. But anyway, so what else do I need to add? There's one more thing. Someone other than the two that have answered so far. I appreciate you guys, but
The tension in the cable, or Is that the components of that we've already broken down?
Well, we have the component broken down on this side, but there's a cable over here too, pulling it over that way. Because if that cable wasn't there, right, it would just swing down.
Right.
This is having a force on the body, so boom, FB, right? And that's entirely in the X direction, so we don't have to break it up at all. No, I'm sorry for this handwriting. Anyway, so FBC. So this is the free body diagram for B, right?
Right.
So that works. Going over to the free body diagram for C,
Right.
what forces do we have?
So
Y to D again with theta.
Right, so we have this force here, but we have it again in terms of some kind of theta, right? So if I was going to break up FCD, right? So I'm going to call this FCD. If I'm going to break that up into its X and Y component, what would the X be?
FCD cosine theta.
Exactly, because it's still the arc touching there, which means the vertical component will be sine theta, right?
Mm-hmm.
CDY is FCD sine. And then we don't know theta. So that we just have to leave there. That's one of the things we have to solve for. This one is FCD cosine theta.
Do we have to dictate like which is negative and which is positive? Because
Well, at the end of the problem, it'll end up working itself out. So like if for whatever reason this cable was actually pushing it down, like that'll work itself out when you do the equilibrium equations. But generally, if it's something like a cable, you should always approximate it as close as you can to where it's going. So in the case, the cable is pulling up, right? Which means that the force should be up and that way.
yeah, I
Like-
understand. I'm kind of more referring to the FABX and the FBC. Like they both point opposite directions. You don't have to say with which one is negative or positive.
I haven't finished drawing it yet, but yes, you would.
Okay.
So at the end, because it's throughout the whole problem. That
Equation, right? Just where they are.
one more time. I'm sorry.
For direction, like you just put it would be negative or positive when you put it in the equations together, right?
Yes, but technically part of a free body diagram is this piece right here.
Okay.
So essentially the idea is that if you didn't give someone a problem, like if I only, at the end of drawing these, if I only gave someone like this piece, right, my actual free body diagrams, they should be able to very clearly see how I got to my equation.
Gotcha.
That means any dimensions should be there if they matter. So like this is a concurrent force system, right? Because every single force at B is acting through B.
Yeah.
We're breaking it up here because it's a two-force member, which means this is a concurrent force system. This is a concurrent force system. So there's really no dimensions we care about.
Should the weight of the stoplight be negative since it's in like the negative Y direction?
Yes, but I'm drawing the arrow pointing down, which by my convention of
Which is negative.
Right.
So
Okay.
once it goes into the, it'll come out negative because of this convention. But when I draw it on my free body diagram, I'm going to leave it positive because as of right now, it's just a magnitude.
Okay. Got it. Thank you.
Okay, yeah, no problem. So going back to C, what other forces am I missing?
Force BC in the left direction.
Mm-hmm. And then one more.
The weight of the stoplight.
Pretend that's vertical. And then again, because the weight of the stoplight is given as a mass over here, it's 15. We're going to do 15 times 10, which, let me find my calculator.
You mean 15 times 9.81?
Yes, 15 times 9.81, because gravity, that's 147.15. again in newtons. All right. Any questions so far about how we got these two? And again, if you have questions, just like scream at me or something because I can't see the chat.
When you're doing the tensions, you have BC on both sides. Should one be CB or does it not matter?
It doesn't matter because it's the force, like the force is the same
Mm-hmm.
here. So that's really why we broke this up, because when you initially look at this problem, you might not know to break it up here.
Okay.
But the whole thing, because if I drew this as one body, right, I would have one unknown, two unknowns, 3, 4, right? I would have 4 unknowns and only 3 equations because it's 2D, which means I couldn't solve it. So I broke it up because even though that adds an unknown, it would still simplify it because here I have 1, 2 unknowns, right? So in just this one, I have 2 unknowns. And then from here, this unknown can be used here, which makes it a known on this body.
Okay, thanks.
In this body, I would have FCD and cosine theta as my unknowns, which makes it super easy to solve for here. All right, so going into the equations, we're going to start with body B because like I just said, we need this one to solve this one. So going into the equations for B, someone who hasn't spoken yet, does anyone want to try to tackle the forces in the X direction?
They equal 0.
They do equal 0 because
Thank God. It's the only part I know.
Wow, good job, Lainey.
what's
Thank you.
then you dug yourself into this hole. Now you got to get out.
I do what?
Now you
Want
got
me
to,
to keep going?
yeah.
But I got the equal 0. That's the most important bit.
No, not really.
You got this. We all believe in you. You can do it.
Lainey.
Especially
Yeah.
if you dip early, you got to contribute something.
I did. I contributed the equal 0.
No, more than that. That's literally contributing nothing.
That's zero of anything.
Okay, put the FAB.
Okay, positive or negative.
Negative.
Okay. And then what else about FAB?
Times
Times.
sine of 15.
So we're going in the X direction, right? Which means
Cosine. That was my B. I wasn't reading correctly.
you are good. And then what else?
And then plus I
So
don't know.
we're looking at here, right?
Uh-huh.
So these are the only 2 forces in the X.
Yes.
What does that say?
You
Oh,
see?
FPS.
Yeah.
See.
My little pen
BC.
is-
Oh, not
I
BS.
can see.
Time. Wait. Yeah.
and that one on the free body or on the problem given was already horizontal, so there's times nothing.
Oh, okay. Times 1.
Good job. So see, you got through it.
Killed
Good
it.
job. Good job.
F of y equals 0. Got it.
Oh, now you got yourself into that again.
Oh. Fudgesicles.
All right.
Uh,
So now
I think PJ wants to do it.
nope, I think he wants to do it.
Okay.
Now we're looking at these 2 forces, right? So how do you
Yep.
into an equation?
98.1.
Positive or negative?
Negative.
Okay.
Times.
Mm,
No, not times. Yeah. Times. No.
plus.
Plus. That's what I meant.
I got you.
Thank you.
Okay.
Then sine, whatever sine is.
Well, it'd be times sine, right? Because
AB times sine. Or does that say AB? Okay.
yeah. All right. Does anyone have any questions on where those equations came from? Lainey,
I
think
killed that shit.
that was beautiful.
I'm not.
Did a great. It was top notch.
Thank you.
Great job.
All right. Any questions? Silence will be taken as a no. Okay. Next step, right? Solve these equations. Who wants to tell me what my unknowns in these equations are?
FAB and FBC.
Okay. There's one more. Nope, there's not. Sweet.
Okay.
Sorry. I
Scared me for a second.
was going to say this FAB, but then I realized you kind of already said FAB. So
That's a secret unknown.
Yep.
Oh, shoot. No. Why do you have to do that?
that's the answer. That's the last unknown. Okay.
Very true.
So which equation would I solve first and why?
FY.
Why?
There's only one variable in it.
Exactly. So there's only one unknown, so I can solve that entire equation because I only have one unknown. So I'm going to move this 98.1 over so that it's already nice and pretty. 98.1 is FAB sine 15. Divide by FAB, right?
Mm,
So then FAB, or no, by sine 15, my bad, is 98.1 over sine 15. Anyone have a calculator?
379.
Yeah, it's 379 newtons.
Sweet. Confirmed. All right, so then what do I do with this?
Plug it into the other one.
Right.
You have to don't you have to put a direction for your force AB?
Well, yes, technically, but that's the magnitude of it, right? So FAB is going to be plugged into these equations.
Okay.
The magnitude of it in the F direction is going to be FAB cosine 15.
Okay.
But let's see. Determine the tension in cables A, B, B, C, and C. Okay, so yeah. So the answer technically is this, right? Because that is the force from A to B. So it doesn't care about the components, so I don't. Does that make sense?
Yeah, I got it.
Okay. So whoever said plug it into the other equation, spot on.
Yay.
Oh, heck. All right, so I'm going to move it over to the other side so that they're both positive. So FAB is 379 cosine 15 equals FBC, right? Take.
366.
Yep.
All right, any questions on how I got those two? So then I already found two of the answers, right? So the answers wanted the tension in FAB, the tension in FBC, and then the tension in FCD, and then the theta for that angle, right? So now my FBC can go over here. And we just said that was 366, right?
Yeah.
Newtons. Sweet. So now, who wants to write the equations for these? Someone who isn't talking, because
PJ.
PJ has been talking the whole time. Someone who's been dead silent.
I'm willing to do it.
Sweet, let's do it.
Right.
Thanks.
Did you want X or Y first?
Let's do X first.
Okay. Well, the sum of fx equals 0, as we know.
Oh, wow.
Since we're going in the right direction, the BC would be negative.
Right.
And then the FCD cosine theta would be positive.
Oh, wow. Sweet. Okay. And then how about in the Y direction?
In the Y direction, since we're going up, the weight is of 147.15 newtons is negative,
Right.
and then positive is the FCD sine theta.
You. Oh. Man, my laptop does not like all this writing. Okay, so boom. What are my unknowns?
FCD.
And theta.
Sweet.
And theta.
Oh, poo. I have two unknowns in each equation. What should I do?
Can you like set them equal to FCD and then just like solve for theta or something? Or
I was gonna say
System of equations.
You could
Um,
divide one equation by the other.
Yeah, use a trig relationship because you have a sine and cosine, so it'll cancel out the forces.
All of the correct answers. I'm going to do it like they did it on the worksheet so I can explain the logic behind how they did it on the worksheet. So there's three trig functions that are all related to each other, right? Sine, cosine, tangent. Tangent relates sine and cosine. So if you're ever in a situation where you have a system of equations like this and you have a sine and cosine and you need to find the theta, use tangent, right? So how can I rewrite? I guess I kind of blew the answer to that, but tangent is sine over cosine, right?
Mhm.
So if
Yeah.
I divide this whole equation by this whole equation, so it's FCD sine theta. Wow. Okay. It is 147.15, right? The whole thing divided by FCD cosine theta is 366, right?
yeah.
So technically what I'm doing is I'm not dividing like the equations by each other. I'm dividing the sides by each other, right? So this side equals this side. So what's nice about this is that, first of all, it'll cancel the unknowns that I don't care about yet. This will become tangent. So then tangent theta will equal some value, right? Does anyone have what that decimal is?
It comes out to about 0.4019.
4019. So then my theta, to undo a trig function, right? To get that theta out, you just use the inverse of that trig function. Is the inverse tangent of point oopsies.
I hit that point a lot.
It's my favorite point, actually.
Point, whoops, I screwed up.
That, right? So anyone with a calculator, what would theta be?
21.9.
So anyone who got an answer of, let me see, of 0.3821, your calculator is in the wrong mode. You are in radians and you need to be in degrees. So now is the time to switch that because we don't really use radians in this class. So that means if between now and then, now in the exam, you use your calculator in radians, please, dear God, to make sure that it's in degrees. Well, yes, it is 21.895. And because this is my answer, how do I write that in the right way? 21.895. How do I write that like they wanted on the exam?
Since it doesn't start with the number 1, you always have 3 sig figs. If it starts with the number 1, it's always 4 sig figs.
Exactly. Okay, so I have my number with the right sig figs. I have my units. What's my direction? Let's go back at the drawing and look and see where theta is. So how would I describe the direction that this angle is? We know it's 21 or 22-ish degrees, right? But how do I
like counterclockwise or something, or
counterclockwise, but from where?
On the positive x-axis.
Beautiful.
Yeah.
Counterclockwise from positive, oh goody, x. Okay, so what's the last thing we got to do?
plug that into one of the other equations to get FCD.
Exactly. Any preference one way or the other?
Let's do the FX one.
Okay. Very fine line of how far in this computer will let me zoom before we can go to shit. So, FCD. Wait, you said the sine one?
I said the X one, but whatever. I mean, doesn't really matter. Like,
Okay, so FCD cosine theta, right? We just found theta. So cosine 21.895. That is not a 5 computer. Equals 366, right? To get that alone, I divide both sides by cosine 21.89, giving me FCD equals what?
394.
394 newtons. And because this answer was asking for the magnitude of the tension.
Real quick, not that it matters too much, but I got 394.5. So if you're rounding to 3 sig figs, it would be 395.
Gotcha. Sounds good. And that's probably just an error with the person before you. I forgot who said it, but the person before you might have used the actual number, like, for, where are the 366?
Yeah, I used 366, so I got 394.46. So that would have rounded down to 394 for me.
Yeah, it's just a matter of rounding, I'm sure. But again, that's close enough to the right answer that you'll be fine. That's just a rounding issue.
Yeah.
All right, so any questions on this problem before we move on to the next one? What kind of time are we looking at? Okay.
130.
Any questions? All right, cool. Moving on to the next problem. So it's up to you guys. Do you want me to go into 3D equilibrium and explain that and do a problem before I do these? Or before I do this one, just so the people who have to leave early can hear one of each? That's kind of what I'm leaning towards.
Sure, I guess that works.
All right, and then that's what I shall do. All right, so real quick, we kind of went over the slide already from before, but still things don't move, so there's no overall force or moments, which means that the sum of everything should be 0, right? That being said, this one's a little bit different than 2D equilibrium in that they have a nice pretty table that's on the reference card that is given to you on the exam for you to use. So the column all the way to the left, the forces, moments, and reactions column, is where you literally list everything right off the bat so you don't forget what you have to include, right? So that's going to be any of your reaction forces. So anything that's at like the forces or at the like supports or at the whatever, at the tension or in the cables. And then there's going to be in that same column any forces that are applied to the body, again, given in the problem. And then finally, there's any moments at the reaction. So I guess technically that's considered a support reaction, but any kind of moments that are either given or at the reactions would go in there too, right? Then for each one in the left column, you find a vector from the point that you kind of care about to the point, any point on the line of action of the force. When I say the point you care about, right? In general, that's the point that's at the origin, or that's the point that has the most unknowns, right? So that would be here because it's at the origin. That would be here because it's got the most unknowns. It's usually the point that everyone labeled as the origin, right? The problem labeled as the origin because there was a reason it did that. So it's generally from the origin to the everything else. Someone is trying to join. Okay, this column in the second column describes how you get from the origin to somewhere on that force. There is going to be an R in this third column too. That R describes how the force itself is moving, right? And then that vector that describes the force's motion or position is what you convert to the unit vector. Again, from lesson 3, it's the force for, or you find the magnitude of the position vector, divide the vector itself by its own magnitude to make it a magnitude of 1, and then you multiply the force given in that problem for that vector into the unit vector so that it has the position that you established, but it maintains its same magnitude. Then, right, this last column is the one that's kind of like the culminating part, right? So for any forces, right, so for anything that had a value in here, you're going to do this column cross this column equals this column, right? Any moments that you had over here aren't going to have anything in these two columns because these are how you convert forces to moments, right? So any moments that you listed over here, so moment reactions, given moments, anything like that is just going to translate exactly over to this column as it's written because you're not going to want to convert them again to a moment because then they're not a moment. So anything that's related to moments goes straight into this column. And if you have an unknown moment, you write it as mx, my, mz, right? Any questions in terms of how you go about filling out this column?
No.
Silence is a no. So, lastly, move forward. So any preference on this one versus this one? This one's a little simpler. This one's kind of complicated.
Let's do the complicated one just so
let's
we
do
can
the
get it
tricky
out of the
one.
way.
Sounds good. Sounds good. Okay, so there's a couple iffy things in this problem, right? Oh wait, I gotta get out of here so I can draw. Okay, so yeah, there's a couple like more interesting things about this problem in terms of how it's kind of set up. So right off the bat, look at your fixtures, right? So this is a ball and socket joint, which means this bar can swing around any way it wants, but it can't at this point move any direction, right? Because it's mounted here, but it can still rotate, which means that all of the forces acting on, or all of the reactions happening here are forces and they're in every direction, but there are no moments because it can spin as much as it wants. So here is going to be an AX, a Z, and a Y. Anyone want to tell me what other forces I have on this diagram that I have to take into account?
The weight of the box.
Beautiful.
The pulley.
Well, the pulley doesn't have its
Tensions.
own force.
The tensions.
But
from
it's,
the point
it's
C.
probably important.
It is. The pulley itself is quite important.
The same test.
Technically, you have a force here, right?
Let's see.
And a force here, right? But, so this is FBD. This is FCD. However, because of this pulley, I don't know how familiar everyone is with the pulley. Like in
It's the same force, right? Because it's the same cable basically going through the pulley
Tension,
system.
right? On the other side.
so the cable, hey PJ, hot mic. But you have the same cable going all the way across this pulley and it's just resting on it, right? The pulley essentially just bends the cable, but the cable itself has the same tension going through it. So FBD and FCD are going to be equal to each other. So we'll take care of that later because technically you still have to account for the different directions, but just know that they are going to be equal in magnitude. So, any other forces you see?
CE.
Yeah, C.
Beautiful. CE it is. All right. So, wow. Yo, I'm sorry for this handwriting. All right. Moving forward. Someone who has not spoken yet. Let me know about what I should put in this column right here, the forces, moments, reactions column. And let me promise you, I will sit here in silence until someone who hasn't spoken yet talks.
A. Moments about A.
Cheater, but okay. Well, not
I'm
moment.
right here.
You already talked.
Oh, okay. It's not me talking, it's my alter ego.
Facts.
That's
Okay.
fair. That's fair.
Anyway, it wouldn't be the moments about A, but you're right that there are reactions at A, right? And because they're all related to A, we can write AX, AY, AZ. Beautiful. Someone who hasn't spoken for real this time.
There would be FBD and FCD, and FCE,
Right.
just the different tension forces, and then also W.
Beautiful. Thank you. And W. Facts. Okay. So now we have all of our forces. Everyone cool with those forces?
Yeah, I do have a small question.
Yeah, what's up?
Like when they give us like the mass of like a weight in kilograms, they know or when they give us like a box that's in kilograms, they give us like the mass, but normally when it's in like pounds or whatever, they give us like the weight in pounds, so we don't have to like cross that, I guess. Is that just like, because I've never seen them give us one where it's like, yeah, here's the mass and whatever units are.
The mass in that system is like ounces, and it's kind of a iffy.
Right.
It's intuitive, you know what I mean? Like
Yeah.
kilogram is. I couldn't tell you the conversion from an ounce to anything else. Or gram. I'm sorry, not ounce. What am I talking about? No, gram. Nope, I was right. Ounce. Gram is metric. Anyway, but yes, you're right. So usually in the pound, feet, whatever, pound, foot, second system, they give you the force already instead of having you convert it from a mass to a force.
Okay. Yeah.
Moving forward, does anyone want to come up with the position vector for this one?
Isn't it like 0, 0, 0?
Beautiful. Can you explain?
Because you're going about point A, which is like, you don't have to move anywhere because the forces about A are at A, so you don't need to move anywhere for them.
Excellent. Someone else, FBD, please. There are 24 people in this room right now. 6 of you are talking.
-3, 0, and 4.
-3. Go this way.
Yeah.
0 and 4. So that was for FBD, and that works because you picked D. Beautiful.
Couldn't you also do 0, 4, 0?
0, 4. Yes, 0, 4, 0. Yeah, because it's anywhere on this line of action, which means you can pick B or D. All right, someone else. CD, please.
FCD would be the same thing as FBD.
Yeah, it's -3.
Very nice. And then FCE. Now y'all actually have to do.
Oh man, math. I don't want to figure this out. This is hard. No.
0, 12, 0.
And what about W?
Same thing, yeah.
Excellent. See, that wasn't that bad.
So just to be clear, for force CD, couldn't you also make that 0, 12, 0 as well because it's still on that line of action, or no?
Uh-huh.
Oh, you
Yeah,
can.
that's
Cool.
what I was thinking.
Yeah, that's what I was thinking too. It's just a little easier.
Well, I mean, I'm going to leave it this way so that, because technically we're going to be doing this calculation anyway, so it doesn't really matter. But yeah, so you can do any point on the line of action. So technically for CD, you could have picked this point right here. I don't know why you would want to, but you could. But so it's anywhere on that line itself.
And you'll still end up getting the same answer at the end.
Yeah, pretty sure.
All right, so this is the kind of tricky one. So for the magnitudes of the force, remember we have to do the position vector and then turn it into a unit vector and then multiply it by the magnitude, right? I'm getting the easier one out of the way. So the forces at A are just going to be as we have them written right now. Boom. So for BD, does anyone want to tell me what the position vector from B to D is?
It'd be D minus B, so -3, and then what?
So I guess
-4 and 4.
okay, so let's see. From B to D. So it'd be -3, -4, and 4. Exactly. So that, right, divided by its own magnitude. So -3, -4, and 4 divided by, what's the square root of that? Oh, it's ugly, isn't it?
16, 32. Oh. So like rad 41.
And then, so that's the unit vector, right? This whole thing is the unit vector. What's the other part that I need?
Multiplied times FBD.
Mm-hmm. Because in this case, the magnitude of the force is one of our unknowns, but at the same time, if we were given one of like an actual value for the magnitude, we could have just multiplied that right here. But again, like he said, FBD because it's an unknown. All right, next one. This is CD. So we're going from C to D. What's the move?
-3, -12, 4.
Yep. Is anyone having issues with how we're getting this number or how we're getting this value?
I just want to make sure. So on FBD, we're going from B to D, correct?
Uh-huh.
So then because D, the position of D is -3, 0, 4, wouldn't it become like, to get to that point, it would be -3, -4, -4?
Exactly.
Oh, I thought there was +4 at the end.
B is at Z equals 0.
Wait, hold on. What did you say?
Because what you have written down is -3, -4, +4. But
Right.
what I'm saying, I feel like it should be is -3, -4, -4, because it's going from B to D.
Right, but that last component is in the Z direction, and from here it's going up, right?
Yeah, I see it.
Okay, so if it was from D to B, it would be -4 at the end, but everything else would also be flipped.
Yeah, I gotcha.
Okay.
Yeah, you're going from B to D, but you take head minus tail, so
Yeah, it's
D
tip minus
B.
tail.
Yeah.
Beautiful. Good question, though. All right, what's the magnitude for this one?
It's like 13, I think.
Can anyone confirm?
Because it's 144 plus
Yeah.
16 is
Yeah,
169.
it does come out to 13.
All right, cool. Not that I don't trust you, but like 13, I think didn't sound very confident.
No, that you're fair. That's fair.
Oh, wow. Okay, that's times FCD again because that's an unknown, right?
Yep.
All right. Someone get me FCE. Or the position vector from C to E.
3, negative 12, 6.
3, negative 12, 6. I agree. Over what?
16.
Yeah. It's like 180, like rad 189.
That's what I got. Did I do it wrong?
No, I mean 144, 36, and 9. so
No,
it'd be
it does come out
189.
to rad 189. I just did the math.
Okay. All right, times FCE, right?
Mm-hmm.
And then W, position vector, please.
0, 0, 12, 0.
0, 0, negative 1.
Yeah. So
Oh, yeah.
0, 12, 0 was the one for the R in the second column.
Right.
You're describing the distance from A. You want a unit vector in the distance or in the direction that the force itself is going for this next column.
Right.
All right, so it's 0, 0, negative 1, but the weight was given, right? Yeah. So I'm just going to write negative 80 here so I don't get confused and think I have another unknown. So there's that. Last column is the first one cross the second one. Again, I'm going to get the easy one out of the way. Oh, excellent. All right. Someone get the second one, someone else get the third one, and so on.
I'll take the fourth one.
Well, I took the fourth one.
I'll take the third one then.
Okay.
I can do the second one. Just give me a second. When I do, I have to divide everything by 13.
Okay. And then someone else do the rest, like do them again so that we can confirm.
So I got the one for the third one, the one that has 13 in for its denominator.
Okay.
So it's a decimal, so I'm rounding. So it's like about 3.69, 0, and then like 2.77.
I have the one below that.
Okay.
5.24, 0, and then negative 2.62.
Don't we also need still those forces on the outside of the brackets still?
Yeah, I was gonna try to scroll over, but I can't, so we're trying.
Oh.
C, D. Yeah, it does that. It gets glitchy.
Got the second one.
All right, what's the second one?
2.49, 0, and 1.87.
0 and 1.8. And that's times F, B, D. All right, so excellent. That's a lot of the points. Almost all of the points. Not all of them, but a severe amount of the points. So the next step is to sum everything in this third column and sum everything in the fourth column. Did I just turn this off? Okay. So then the next step is to sum these and these. So, but before you do that, so those are where your equations come from, right? before you do that, take a very quick look at where you want to start, right? So every single time you get one of these problems, this table is going to be ugly, right? We have 1, 2, 3, 4, 5, 6 unknowns, okay? And then in this column, if I were to sum all of these, each of these equations would have 1, 2, 3, 4 unknowns in them, right? Which sucks. If I were to sum these equations, they would have 1, 2, 3 unknowns, which is a little bit better, okay? That's fine. What happens if I were to, remember that assumption we made at the beginning because of the pulley?
Mm-hmm.
So,
B is equal to FD, or FBD is equal to FCD.
So we
right.
just write them as the same force.
Right. I'm just going to call them FD so I don't have to rewrite the whole thing. So now this is the same force. Another thing to realize, we couldn't solve it before we broke this up because we have 3 equations and 3 unknowns, but this whole equation here is just 0 equals 0, which is useless. So all of these values are useless to us. And that's only the case if the entire column is 0. Does that make sense? Why we
Right.
solve it like
Yeah,
that?
that would be the moment in respect to the y, right? Because that's how it was done on the notes.
Uh-huh. So then the moment with respect to the y is 0, which means it doesn't rotate in the y at all.
Gotcha.
So now we have FD and FCE as our unknowns, which we can do because we have 2 equations. So someone let me know what the moment equation for x is.
Here, I can do that one real quick.
Sweet. Now I'm going to call, oh, we already did that. Okay, just kidding. Equals 0 because things aren't moving. All right. What would my equation be?
So it would be 2.49 times, wouldn't you'd multiply that by force D, right?
Mm-hmm.
Then plus 3.69 FD
Mm-hmm.
plus 5.24 FCE and then minus 960.
Beautiful. So I want to rewrite that so that my constant is on one side and these 2 terms are combined. So it would be equals 960, right?
Mm-hmm. And we combine that, so it'd be 2.49 plus 3.69, which is 6.18 FD, and then plus the 5.24 FC.
5.24 FCE. Beautiful. Someone get me some of the moment in Z. Do you want me to scroll back up?
Yeah, that'd be great. Thank you.
0.
I'm just going to combine them right now.
Okay.
Oh, wait. Okay, so it'd be 4.64 FD minus 2.62 FC, and that's equal to 0. So we don't need to rewrite anything.
Exactly. So now I have these 2 equations, right? I can either solve it with substitution, or I personally like to solve it with a matrix on my calculator because it's just plug and chug. Does anyone want me to go over how I solve it in my calculator?
Yes.
Okay. So the first step you got to do is you have to make sure that your constants are lined up. Oh, that went well. Okay, that your constants are lined up and that your everything else is lined up. So everything should be stacked based on what the essentially what the variable is. So here FCD is my unknown, so these should be on top of each other. And then these should be on top of each other, and then the constants should be on top of each other. Then I'm going to go into my calculator and make a, I can't remember if it's a 2x3 or a 3x2, but it's the one that has 3 across the top and like 2 rows. So then what I'm going to do is I'm essentially just going to write a vector that resembles these equations, but without any of the variables in them, right? And then that's going to be my constants, right? So everything in the first column is going to be the coefficients in front of FD. So the first one is going to be 2.49, and the second one is going to be 4.64. Everyone see where those numbers came from? That's just here and here. And then the second column is going to be what? Someone tell me.
Should it be 6.18 instead of 2.49? Because it's
See, this is why I'm not taking this class. 6.18. Very true. Good catch. All right, someone else tell me FCE.
5.24 and then negative 2.62.
Beautiful. Negative 2.62. And then constants are the same thing. You just write the top one and then the bottom. Oh, what the heck? And 0. Okay. So then once you've made this this matrix, right? Second quit. And then go into matrix and then math. And there's something called RREF. Reduced row echelon form. That's some super complicated math thing that I don't understand at all, but it solves my systems of equations for me, so I love it. So then you're going to do that and then select this vector. So whatever letter you assigned this vector, right? You're going to put that here. So if we call that A, you're going to put that here. Right? And then it's going to spit out another vector at the bottom, right? Your answer is going to be another vector. It's going to have a 1 here, a 0 here, and then a 0 here and a 1 here. And then these numbers are going to be the solutions to your system, right? So the top row will always have a 1 in the beginning, right? So that means that it's telling you that FD equals whatever this number equals.
Where do you find that command for the reduce that double REF?
What calculator do you have?
TI 84 plus.
Okay, so if you go into second matrix, after you it's the tab that's math.
Oh, okay.
And then it's letter B.
Oh, found it. Thank you.
Yep, you're good. So then once you plug that matrix into that command, it'll spit out, like I said, 1 0 number and then 0 1 number. The row or the column that the 1 is in is the variable that constant is the solution to, if that makes sense. So if the 1 is in FD, that constant will be the solution to FD. Also, all of this is to say that if none of this made sense to you, you can still do it by hand. I just don't do math by hand because I'm bad at math. So I make mistakes all the time.
Isn't there another way you can do this matrix multiplication? Like if you make A like a 2 by 3, and then you have the products as like a 1 by 2, and you do like the inverse of A times B, you'll get the answers too?
Yeah, I think so. I don't understand how she does that or why she does that. So
yeah, I did it like once in Liao's class, and it worked, and I got the answer. So I mean, that's also a way you can do it too.
Yep.
Does this RREF work with like a normal 2 by 2 matrix, or just with like 2 by 3s?
I think it's with 2 by 3s. I don't really know though. I've only used it with 2 by 3s because usually systems that they have you solve by hand are only like 2 equations with 2 unknowns.
Right.
So does anyone have these solutions? Did anyone actually do that?
I did it. I don't know. Which one did you say was which again?
So you see how you have a 1 0 and then a 0 1?
Yeah.
Mm-hmm.
The 1 is here.
Mm-hmm.
Number is the solution for FD.
Oh, okay. Then that one is 62.1.
Yeah.
And then for FCE, I got 109, or it would be 110.0 because it's like 109.97,
Yeah.
so it rounds up.
Oh, yeah, 110.0.
Yeah, it's 4 sig figs.
Yeah.
Beautiful. So that and that also. Yeah. Okay. So these two are two of our answers, right?
Yep. And now we plug them back in with the force equations.
Exactly. So, let me get out another pen. Do you guys actually want me to do out these force equations, or are you confident with me doing it because once you do that, it's just one unknown. So it's like once you substitute this in, it's just you add straight down and get AX. So do you want me to do that? I don't.
I think that's not bad. I can probably do that.
Yeah, it's not too bad.
How's everyone else that's being silent feeling? I know you guys can add and subtract, so I don't want to sit here and waste your time with stuff you might actually be getting stuff from. Okay, silence means it's a go. Cool. So before I jump back in and do these last problems, if you guys want me to, I'm going to go into here and kind of go over the last couple of things that I wanted to do. So everyone, when you came in, unless you came in late, I didn't have you do it when you came in late, but everyone that came in on time did an entry like Kahoot thing. Go back in and retake that Kahoot, but use this game code. It's the same questions, so it's kind of skewed, but it's fine. It shows that you either learned something or memorized the answers. And then a couple things I wanted to go over while you guys do that. If you could do that now, that'd be great. Before the exam, this is how I recommend it. So if you are still struggling with a topic, so say you still really don't get to the equilibrium, sit in front of the lesson worksheets that we did in class, right? Try to solve them. And if you get stuck, look at the solutions. They're posted. Once you feel more comfortable, try the homework questions, right? Because the homework questions are probably just a little bit more complicated, but not by much. Then go on to, once you're ready, use the exam questions or the review questions as practice tests, right? So these are literally past exams. So print them out, staple them together, sit down, time yourself without looking at anything, given exactly what you're going to get on the exam. And then see how you do. Once you're done taking the practice exam, look at the solutions. If you got stuck, figure out where to go, blah, blah, blah. But don't do that while you're actually looking at the worksheets the first time. You know what I mean? So I don't think anyone, I don't think the professors like to stress this enough, but this is a tough class, right? You're literally learning how to A, look at the world completely differently, and B, do the math that shows how you see it now, right? So it's a tricky class. So it is possible to do well. It's just a matter of your grade will essentially be, except for a lucky few who get it on the first pass, your grade's literally going to be a function of how much time you put into this class. So knowing that you have 3 days to really kick it into high gear and study for this exam. It sucks, but let me tell you how if you turn on the TV and just sit here and do worksheets, your grade will go up at least 25%. So doing the worksheets over and over again will make essentially muscle memory. So there's that. So anyone who wants to leave after they've submitted the Kahoot post-test thing, just go ahead and put your name back in the chat so I can verify that you were here for the whole length of the meeting. And then from there you can head out and then
Real quick,
yeah.
how do you access the practice exam that he showed us in class?
How do you access it?
Yeah.
Yeah, okay. Am I still sharing my screen? I think so.
Yeah.
Okay. So if you go to the Canvas homepage, right? You're on your dashboard.
Yeah.
No one laugh at my grades if they pop up. Okay, cool. So there's that. You go into modules. And then in module, I think 12, yeah, it's statics review 1. All of these are the worksheets, okay? The solutions are posted. Please, dear God, do not look at the solutions until you're done taking one of these exams, and then looking at it to grade it, essentially.
Mhm.
But yeah, that's how you access it. Like I said, these are literally 3 exams. So 1 through 3 was exam 1, 4 through 6 was exam 2, and 7 through 8 was exam 3. 7 through 9, I'm sorry. So if you put these out, you literally have 3 practice tests that you can time yourself and do.
Thank you.
Yeah, for sure. Anyone who wants to say, I'll do another practice problem, but oh wait, are they locked?
There was a question mentioned in the chat. I don't know if it ever got answered, but are there going to be couples on a 3D equilibrium question?
Not that I know of, because I think that's more of like a 2D kind of thing because it rotates in the same plane as the forces are being applied. So I don't really know how relevant that would be.
Okay.
Yeah. Will there be 3D? Yeah. Yeah. No. Okay. Sorry for not answering that. I just couldn't see the chat. Okay, and then also, apparently the solutions are locked, but that's definitely because it's so A, you guys work on them ahead of time, and then B, so that cohort A, when they do all that in class on Monday, they don't look at the solutions beforehand. Because if there was any worksheet to like force yourself to suffer through, it would be these 9. Okay, so again, anyone who wants to scoot, you can scoot, but make sure you put your name